Swayam Prabha. Digital India. Educated India.
So let's now look at implications, few more implications of strong convexity. Okay. So let F be strongly convex. So let's look at this proposition. Then the following are equivalent. So the first condition is the usual definition of strong convexity, which is f of y okay. So if I consider g of function g of x defined to be f of x minus mu over 2 norm x square. So if f is strongly convex, then g of x is going to be convex. So this is the third sort of equivalent definition is and the fourth equivalent definition is f of lambda x okay. So let's revisit the statement. So let's say the function f is strongly convex with modulus mu greater than 0, then all these conditions are equivalent. Okay, so all these are equivalent definitions of strong convexity. I mean, this is something that we already know, and what this first sort of characterization says is that the function sort of the difference between the when we write the first order condition, the difference in some sense the function sort of moves upward by at least this much amount, right? So that's the first condition. The second condition is if you have an f like a function which is strongly convex, and even if you subtract a quadratic kind of function from that, basically you subtract mu over 2 norm x square, that function, even though it need not be strongly convex, it is going to be convex at least, right? So when we think of strong convexity, that means the function has a like always, as I said, always think of a quadratic function when you think of strong convexity. So even if you subtract this quadratic type of function from this original function, you are still going to be left with a convex function. So that is the second sort of yeah.
Like if we are removing mu by 2
Mm-hmm.
x square, like why can't we say it's strictly convex?
Strictly convex what? I mean, that need not be true.
But if we are taking the HCM
Mm-hmm.
more than the
I mean, it's so all we know that the Hessian of f is greater than or equal to mu times identity, right? And for the other one, it's also going to be mu times identity. So we cannot say it's strictly greater than 0, right? So had this been strictly greater than mu times identity over here, then you could have said that, right? So we are going to prove this as well. But the third condition, what this says is, suppose I apply Cauchy-Schwarz on this, right? On the third condition. So A transpose B is going to be less than or equal to norm A times norm B. That's Cauchy-Schwarz and using Cauchy-Schwarz. And one of the norms would be norm of x minus y. So what we say is that difference between the norm of the difference of the gradients is going to be greater than or equal to norm of the like basically the difference of x basically x and y, right? So An implication of this would be right. So this is one of the conditions, which is, I mean, basically the implication of this third one. And fourth one is again something that we had looked at, where the right hand side we know that exceeds the left hand side at least by this much amount. So all these are equivalent definitions, and we are going to prove this. So if we need to show that these are equivalent, so our proof strategy would imply that if let's say I show that 1 is equivalent like to 2, and 2 implies 3, and 2 also implies 4, then we are done, right? Because we have shown that all of these are going to be, I mean, or I think one thing that you possibly need to show is that 4 is also equivalent to 1, but I'll probably leave this as an exercise, but then you will be done, right? So this particular result is going to be important. In fact, you will see that in most of the proofs. So let's try and show that 1 is equivalent to 2. So what is the gradient of g here? So what is gradient of g of x? Gradient of f minus mu x, right? So g is convex. You have okay. So g of y by definition is fy minus mu over 2 norm y square. G of x is f of x norm x square, and the gradient is okay. So we are almost there. So what we have received is, what we have now is minus mu over 2 norm x square plus mu over 2 norm y square and then you have minus plus mu times norm x square, right. So plus mu minus mu by 2 gives you again plus mu by 2, right, and then you can do the square completion, and this turns out to be f of x plus this term minus plus mu over 2 times norm x minus y square, and this is the first sort of characterization of the strongly convex function. Is this clear? So again, minus mu by 2 x norm x square plus mu x norm x square, this gives you plus mu by 2. You take mu by 2 common, so that is norm x square plus norm y square, and then you have, wait, I think there's another, yeah, there you have another term here, sorry, my bad, minus mu x transpose y, right? So if I expand this, you have norm x square plus norm y square minus 2 times norm x transpose y, and this is, any questions on this? Right. So if G is convex if and only if this is true, so G is convex if and only if f is strongly convex, or this 2 is true if and only if x is 1 is true. Okay, right. So how do we show 3? So let's say we want to show that 2 implies 3. Again, this gives you an idea as to how we can sort of and when you want to prove the results of this form, what kind of simple tricks that you can use. So remember, like here we have to collect terms of the form gradient of f of x and gradient of f of y, and from, if I want to go from 2 to 3, then I probably need a gradient of g as well, right. So that means I would have to use the condition for convexity for g, first order condition for convexity of g. We know that g is convex. So if g is convex, then gy is greater than or equal to g of x. Okay. I can equivalently write this as g of x greater than or equal to g of y plus gradient gy transpose x minus y. right? Because I mean x and y I can simply interchange, and if I add these two equations now, this basically gives me 0 greater than equal to and I mean taking this to the left hand side, this basically tells you that g of x minus g of y transpose x minus y is greater than equal to 0, and you just use the gradient definition of g of x and you get this inequality. Okay. And the final thing is something that I mean we need to show this particular result. Again, it follows sort of naturally from like if we use this. So, this particular result is often used in proving other results, and more than anything this result is often used in proving other results. And the way you can, if you want to show that 2 implies 4, we basically need to use the other definition of convexity, which is f g of lambda, like if g is convex, then g of lambda x plus 1 minus lambda y is less than or equal to lambda of g of x plus 1 minus lambda of g of y, right? And by definition this is nothing but f of lambda x minus mu over 2 and again if I expand this in terms of definition of if you take this term to the right hand side and do some simple algebraic manipulation, you can simply show that this is less than or equal to lambda f of x plus 1 minus lambda f of y. So, I mean, so we are done. Okay. So, as I said, like you can, so this particular result, this particular definition of strong convexity, it's often used in proving other results about strong convexity. Any questions on this? Yeah. This to here? Yeah. Lipschitz continue. Yeah. Not should not be. I mean, you can still upper bounded by some L, but you can also lower. Lipschitz continuity is about the upper bound on the gradient, or upper. Yeah, this is about the lower bound on the. Well, Lipschitz continuities are not upper. Like so, again, we really need to specify what Lipschitz continuity is defined on. So, does everyone know what Lipschitz continuous functions are? So, usually we define Lipschitz continuous function so we say that f is L Lipschitz if x minus y or y minus however you want to write it. This is the definition of Lipschitz continuity of a function, right? So, in some sense what you want to say is that the norm of the gradient is upper bounded by L. We also define something called L Lipschitzness of the gradient and not of the function itself. So, we say that we call this L smooth or functions with Lipschitz gradient, and in fact we are going to look at this condition as well, which says that norm of the gradient of f of x minus f of y that is less than or equal to L times x minus y. So, in this case the function is not Lipschitz continuous, it's a gradient which is Lipschitz continuous, okay, the gradient of the function which is Lipschitz continuous. So, such functions are called L smooth functions. And if you look at strong convexity, this is the opposite of L smoothness. So, in some sense you say that it's upper bounded by this, but it's also lower bounded by mu x minus y. So it's kind of sandwiched between the two. And if you look at a function like x square, L and mu turn out to be the same. So if the function is L smooth and mu strongly convex, we know for sure that L is greater than or equal to mu. That's one of the implications of this thing, right? Because we know that this is lower bounded by, from the definition of strong convexity, this is lower bounded by this. From Lipschitz gradient or L smoothness, it is upper bounded by this. So L has to be greater than or equal to mu. First, for quadratic functions, L is exactly equal to mu, but in general, L is always greater than or equal to mu. And this is what, and if you look at x square, it is both Lipschitz, it is both L smooth and mu are strongly convex, with L and mu both being equal to 2, right. So that is the distinction between Lipschitz smoothness and strong convexity. Is everyone able to follow? Okay. So as I said, one of the so strongly convex functions, I mean, other than the different mathematical characterization that we looked at for strongly convex functions, one of the things that strongly convex functions are really useful in is this particular fact. So let's say you have two functions, let f be mu strongly convex, okay, and another function is g, which is simply convex. Okay, so you have a strongly convex function f and a convex function g, and you define a new function h, which is basically the sum of these two functions f and g. So what you can say is that not only h is strongly convex, in fact h is mu strongly convex. So suppose I want to optimize a function g, and in some way I am able to come up with a function f which seems to share the same optimal solutions as g, but behaves like a strongly convex function, then I would rather work with this function h, right, and because this function is going to behave like a strongly convex function. So again the idea is, so I mean a quick simple proof. So we want to show that h is also mu strongly convex. We know that f is mu strongly convex and g is convex. So what is h of lambda x plus 1 minus lambda y? By definition, this is f of lambda x plus 1 minus lambda y plus g of lambda x plus 1 minus lambda y, right? And we know that f is strongly convex. So this would be, because f is mu strongly convex, this would be less than or equal to lambda fx 1 minus lambda fy minus mu over 2 lambda 1 minus lambda. And because g is convex, we know that this particular term is less than or equal to lambda g of x plus 1 minus lambda g of y. Now I can add these numbers, add these functions, lambda fx plus lambda gx, which is equal to lambda of hx. So that means this thing is less than or equal to, your left hand side is less than or equal to lambda of h of x 1 minus lambda h of y minus mu over 2 lambda 1 minus lambda, and this is the definition of strong convexity for h. So not only h is strongly convex, in fact h is mu strongly convex. Okay, so that completes the proof. So one of the implications of strongly convex function, if you add basically if to a convex function, if you add a mu strongly convex function, the resultant function is also mu strongly convex, and that also kind of proves this particular part, right? We know that this function is mu strongly convex, right? If g of x is convex, or if g of x is convex, so mu strongly convex plus convex would imply that f of x is also strongly convex. Okay, so that's one.
If both f and g are strongly convex,
Yes.
we can conclude that their summation will be 2 times 2 mu.
Yeah. So yeah, 2 mu is strongly convex. Yes. So another implication, something that we already discussed, is that strongly convex function. So strong convexity implies PL inequality. Okay. So another proposition. So we assume that f is mu strongly convex. This implies f satisfies where f star is defined to be the optimal f of x star. Okay. So let's take a look at the proof. All right. So again, if I were to show something like this, it's in terms of the gradient of f, right? So that means we would have to use a definition of strong convexity where gradient comes in, and that is we know that, let us fix y, right? Let's fix. So f of y we know is greater than or equal to f of x for all x. Okay. So we want the result in terms of gradient of f of x. So that's why we are using this particular definition of strong convexity. So far so good. All right. So this holds the left hand side exceeds the right hand side for a specific value of y, right? So that means if I try to minimize the right hand side, it would also hold true for that, because right now it holds true for this particular specific choice of y. Now if I look at all possible y's for which the right hand side gets minimized, it would also hold true, right? So that means fy is greater than or equal to minimum over y okay for all x. That's true, right? So if we want to minimize it with respect to y, we have to set the gradient with respect to y to be 0, and this gives us the condition the optimal y must satisfy this, right? Because if this needs to be minimized, the optimal y must satisfy this for the right hand side. Okay, so which basically tells you that so y at like the optimal solution, this y minus x is nothing but, so y minus x is negative 1 over mu, this thing, right? So from here, if I substitute this, I get f of y is greater than or equal to f of x plus gradient of f of x transpose y minus x is minus 1 over mu plus mu over 2, and then again minus 1 over mu square okay. So this from here you get negative 1 over mu norm like norm square, norm gradient of f norm square, and this is 1 over 2 mu, right, plus 1 over 2 mu. So basically you get f of y is greater than or equal to f of x okay, just adding these two terms. All right, or what do we have? 1 over 2 mu norm, or in fact you can directly argue from here. So this holds true for any y, right? Like we had chosen as, like we had fixed y in the beginning. So this holds true for any y. So this would also hold true for if I try to minimize the left hand side with respect to y. So it would hold true for that as well, because this holds true for any y, and this is nothing but f star, your optimal value, right? So f star is greater than or equal to f of x minus 1 over mu 2 mu, or which is your PL inequality. Okay. Is this clear? This one here. So this is, I am trying to characterize the value, find the value of y for which this gets minimized, right? So that means I need to take the derivative with respect to y and set it to 0. So if I take the derivative of this with respect to y, the first term is gradient of f of x, The second term is y mu times y minus x, and this needs to be set to be equal to 0, and you get this particular optimality condition for okay.
Does that entire inequality hold for that particular y?
Yeah, so it holds for a specific y, as I said, like you fixed y and then you change your x, right? So this entire inequality holds for one specific y. But if I choose a y for which this whole thing is minimized, so it would hold for even that one as well, right? If I am able to now, let's say, choose another y.
We would also have to input that same y on the left hand side, right?
No, so this inequality would be, you are right. So again, the question is, this inequality holds for a specific value of y? Yes. So let's say I have chosen y to be equal to 5, and we know that for y equal to 5, this inequality holds true. So this particular term has a value for y equal to 5, but if I had chosen y something else, I may even make it even smaller, right? And that is what I am doing. Okay, so I'm still keeping the left hand side to be fixed, but I'm trying to choose another value of y, so that it becomes even smaller. So in some sense, if you search over, this y belongs to a feasible set, and if you search over a larger set, you can find a better minimum, right? And that is what we are trying to do. Any other questions on this? And using this particular PL inequality, you can show that functions like x square plus 3 sine square x, this satisfies PL inequality. But as we looked at the plot of this particular function, this is not even convex function to start with. Forget about it being strongly convex. Okay. This is a very special class of function, as I said, because lot of you can provide certain convergence guarantees for these class of functions, even though these functions are not strongly convex. And only I think starting on maybe 2016 onwards, people have started to explore more on the PL inequality side, because whatever you can guarantee for these class of functions, you can in general generalize it. You can generalize it for strongly convex functions for sure, but you are also covering a broader class of functions. So that way it's all right. So this pretty much sums up the discussion on strongly convex functions and its implications, and we will revisit all these implications later when we try and design algorithms. But for the remainder of the class, let's try and look at the first order condition for optimality for convex functions. So let's revisit the mathematical optimization problem. So or optimization problem. Okay. Suppose we are looking at an optimization problem of this form. Your x is some feasible set, some capital like this cursive x is some feasible set, and we want to minimize this function f of x. So what is the first order condition for optimality? Let's also assume that f is convex. So let's say x minimizes if, so what is the first order condition? Okay. And so let's look at the geometrical interpretation of this particular condition. Now suppose let's say you have a constraint set which looks something like this, right? This is your x, and you have a function f, and let's look at the level curves of that function. Let's say this is f of x equal to 0, f of x equal to 1. So you just look at these level curves. Okay. So when is this function minimized subject to x belonging to this particular constraint set? When would that get minimized? When it just touches this constraint set, right, of feasible solution set at this point. Let me also make this statement complete, and this is true for every y in your feasible set. So what this condition, so function is increasing in this direction, right? So the function is increasing in this direction. That means the gradient of this function would be pointing in this direction. So if x is your optimal point, and I choose any y in this constraint set, so this is your y. So the angle between these two vectors is less than 90 degree, and that is what this particular condition is saying. Okay, so that's the geometrical sort of interpretation of this particular statement. Is this clear? So the inner product between two vectors, these two vectors is greater than or equal to 0. That means the angle between them is, it's an acute angle. The angle between them is less than 90 degree, and that is what this particular condition says. Yeah.
What did you mean when you said touches?
So this is the optimal solution, right? Yeah. So it's when, I mean, when this particular level curve touches the constraint set, I mean, you can keep increasing. Even this would be, I mean, in this case, for instance, f of x is 0, 1, 2, 3, and so on. So you want to minimize f of x, and it gets minimized when this level curve touches the constraint set. Okay, and because the function is increasing in this direction, so gradient will be pointing in this direction, and you have another vector y in the constraint set, and then the angle between these two vectors is less than 90 degree, less than or equal to 90 degree, and that's the first order condition for optimality.
So we are assuming that our constraint set is also convex.
Yes, so we are looking at convex optimization, so that's a good point. So constraint set, let's also make it clear that x is a convex set. Okay. Why convexity of x is important? Well, if I look at a similar sort of picture, let's say x is your constraint set, x is not convex. Okay, so it may look it's not convex, so it may look something like this. So this would be an example where your constraint set x is not convex. And if I look at the level curves now, right? So this would be the optimal solution, let's say. But if I choose, and the gradient is pointing in this direction, if I choose a point somewhere over here, this angle can potentially be more than 90 degree, right? So this would not be the first order necessary and sufficient condition for optimality. So for convex functions, when you're trying to minimize convex function over a convex set, the first order condition for optimality is this particular condition over here. Is this clear? So if you are working with unconstrained optimization, let's say x turns out to be this convex set, x turns out to be Rn. So what is the condition for optimality for unconstrained optimization? Gradient is 0, right? And you can also see it from here, right? So if x is a whole of Rn, then the vector is also making positive, I mean acute angle, and also making an obtuse angle, right? I mean, because you can move in every direction. And for this to be, I mean, if you just replicate this condition, I mean, you will have y minus x greater than or equal to 0 and also less than or equal to 0. So the only way this is true is when gradient of f of x is equal to 0. So for unconstrained optimization, the first order condition for optimality is okay. Is this clear? And that's precisely because, I mean, the point will be a strictly interior point in this set, because x is whole of Rn, right? It will be an interior point, and you will, I mean, basically it will make all types of angles. So the only way this is true is that the gradient of f of x vanishes. Okay. So the condition, the general condition is x is optimal if and only if And let's take a look at an example which is on quadratic optimization. We want to minimize subject to this linear equality constraint. So, what is the first order condition for optimality for this particular quadratic optimization problem? So, what is the gradient? So, in this case f of x is of x transpose qx. So, we also assume that q is, I mean this would make sense when q is positive semi-definite, right? Otherwise, it is not even a convex problem to start with. Why do we need q to be positive semi-definite? We want this function to be convex, right? And what is the second order condition for convexity? The Hessian should be positive semi-definite, and in this case Hessian is exactly q. So, we want this q to be positive semi-definite, and that is one of the requirements that we have for convex optimization. So, what is the gradient of f? Okay. So, the first order condition for optimality is, let us say x star is optimal. So, gradient of f of x evaluated at x star. So, that means qx star plus c y, this should be greater than equal to 0 for all y in the constraint set. The constraint set is defined by the equality constraint Ax is equal to b, right, or Ay equal to b rather. Okay. So, this is the first order condition. Another way to look at this is, we know that Ay is equal to b because y is a feasible point in a constraint set. Every optimal solution or optimizer is also a feasible point. So, Ax star should also be equal to b. Okay. So, that means a y minus x star, this is equal to 0, right, and if we call this z. So, in some sense, or you can basically, so if x star, yeah, right. So, what you can do is, z lies in the null space of A, okay, because this is true for any y, right. So, you can also equivalently write, write it like this, and if the null space is vacuous, then that means, it is an unconstrained optimization. So, we know that qx star plus c is equal to going to be 0, and the optimal solution x star is simply going to be negative q inverse c. This is for unconstrained optimization. Okay. Is this clear? Thank you for pointing this out. This should be y minus x star greater than equal to 0, and yeah. Because y minus x star, we know it belongs to null space of A, right? So, this is the condition, equivalent condition. So, for every z belonging to null space of A, this should be greater than equal to 0.
We are proving this using that or?
No, so we know that x star Ax star equal to b, Ay is equal to b, because both, both optimal point and optimal point is also a feasible point, right? So, that means Ay minus x star is equal to 0. So, y minus x star, they should belong to the null space of A. And if I consider because this is true for any y, so I can pretty much look at the null space of A, right? So, for any z in the null space of A, if this is greater than equal to 0, then this is another characterization of the optimal x star. So if this is going to be qx star plus c, so in a product between qx star plus c and the null, like any vector in the null space of A, if that is greater than or equal to 0, so that would be the first order condition for optimality. And if the null space is vacuous, so that means that is you are in unconstrained optimization case, and then in that case x star turns out to be simply negative q inverse c.
If null space is only 0 vector, then my problem is too much constraint, right? Because ay equals to b, a equals to b.
Then you just have one feasible point, which is only going to be one which is the optimal.
Then it won't be a constrained optimization, unconstrained optimization.
No, it will be a constrained optimization. I mean, just that your constraints contains just one point.
No, I'm saying unconstrained because we have written.
Yeah, no, I'm saying that the null space is vacuous. Like as in, like, let's say A is all zeros, A is all rows. I mean, basically A is, I mean something which is trivially satisfied, right? So then it becomes an unconstrained optimization. So if if this equality constraint is not even there to start with. Yeah. No, I'm saying that if you are in if it's a constraint, that's what you can say. But if, let's say, if you are solving this problem in an unconstrained, like without this equality constraint, then the optimal solution turns out to be this, if q is invertible. So in fact, let me also make it q not greater than q is strictly positive definite, so that we can consider inverse of q. So for unconstrained optimization, we know that the gradient vanishes, so that means qx star plus c is going to, so this is true only for unconstrained optimization. Yeah. So the solution in general, really depends. So this is the solution, right? This is how you characterize. No, we find x star which satisfies such that for any vector z in the null space of A, this is satisfied.
Okay, for all the vectors.
Yeah. Okay. So we are going to look at, like in this starting next lecture, we are going to look at ways to at least, if you have a constrained optimization problem, convert them into unconstrained using something called Lagrangian methods, and then try to find the optimal solution that way. So we are going to look at we are going to look at ways to solve these optimization problem, both analytically and then using whenever the functions are nicely behaved, or either using numerical methods. As of now, this is just the characterization of the optimal solution.